Hello everyone. So in this video I just wanted to give you an idea of how I collected data for the Ballistic Pendulum experiment. So the goal of this experiment is to calculate the velocity that this ball leaves the launcher at two different ways. So one way is just using kinematics. So I'm going to fire this ball. I have a piece of carbon paper over here, so it'll leave a mark on the carbon paper. And if I know the distance from when it leaves the mark to the edge of the gun, I can measure that horizontal distance. That's going to be my horizontal displacement. And then knowing the height of the gun, again using kinematics, I can get the time of flight of the ball. So the time it took from when it left the gun or the launcher to when it hits the table here and leaves a mark on the paper. And then if I know the horizontal displacement and I know that time, then I can calculate the velocity, right, the average velocity. But we know with a projectile that the velocity in the x direction is constant. So that velocity that I calculate must be the initial velocity that the ball leaves the gun at. So that's one way of calculating the velocity. Let me just show you one of these launches. These guns are a lot more powerful than the wooden guns that we used before, and they're also a lot more consistent too. Make sure it doesn't roll. So I just fire this, it hits the paper, leaves a mark, and then I can simply measure from that mark to the edge of the gun here. Okay, and really I want the horizontal distance. So I can estimate what this distance is first. So this is actually the way I did it. I measured this distance, and then from the mark to the edge of the box here, right? And then added that distance back. So I have actually the horizontal distance, which is what I want. The second part, or the second way of determining that velocity, is using both conservation of linear momentum and conservation of energy, right? Those two theoretical ideas. So in this case, what we're going to do, take this down a little bit so you guys can see this. We're going to launch the ball again, but now it's going to embed itself into the pendulum here. So during that collision, because there's no net external other forces acting on the ball of the pendulum, we assume that linear momentum is conserved, okay? And then when the pendulum swings up to its highest point, again, we're assuming that this has very low friction here in the axle. So we can assume that we have conservation of mechanical energy. So if I calculate the potential plus kinetic at the initial time right after the ball collides and it has some initial velocity, they move together with some initial velocity, I can calculate that mechanical energy. And at the highest point, right, the pendulum and ball, that combination has no kinetic and all potential. But I can calculate that final mechanical energy. So use the fact that mechanical energy is conserved and linear momentum is conserved, and that will give me the velocity of the ball as it leaves the gun. Okay, and I'll explain this more carefully in the video lecture. Right? I just want to show you how I collect the data. So actually, let me just do one of these. So I'm going to get this ready to go. Now it's very important that you move this. There's an indicator here for the angle. So put that down to 0. And then I'm going to launch it. Right, so it embeds itself in. It doesn't go up very high, and it's really hard to tell. Right? In fact, it's only like maybe a few millimeters, so there's really no easy way of measuring that height change. So we're going to do it indirectly by measuring the angle. Well, when this launches in, right, and displaces it, it leaves this little indicator at whatever angle the highest point was, so it can read out that value. It tends to be around 8 degrees or 8.5 degrees, 9 degrees. It depends on the individual ballistic pendulum. In our case, it's around 8.5 degrees. Okay, and by knowing that angle, then I can calculate the change in the height, and that will allow me to find the change in potential energy. All right, so that's the basic idea. Again, two different ways where we want to find the speed of the ball as it leaves the launcher. Great, thanks.